All right, I think we can probably go ahead and get started at this point. So it's a pleasure today to welcome Romy Rodriguez Martinez to give our lunch talk. So Romy is a grad student at The Ohio State University, where she works with Scott Gowdy on detecting and characterizing transiting exoplanets. And her research really focuses on trying to understand the composition of terrestrial exoplanets, and she will tell us all about that today. So over to you, Romy.
All right, thank you so much, Andrew, for the introduction and for the invitation to speak here. Very excited to be here. Can you all see my screen and hear me okay?
Looks good to me, yeah.
All right, so I'm gonna go ahead and start. So hi everyone, today I will talk to you about my work that I've been doing with Professor Scott Gowdy at Ohio State University on constraining the interior structure and composition of low mass planets. And before starting, I wanted to acknowledge my wonderful collaborators, and in particular my advisor, Scott Gowdy. So over the past couple decades, we have discovered literally thousands of exoplanets. And you can see them here plotted in this mass period distribution, where you can see all the planets that we've discovered so far, color-coded by their detection method. And you can see that these planets span a really wide range in their masses and periods. And we're now nearly at almost 5,000 planets, while many more thousands await confirmation. And one of the most surprising discoveries in this field of exoplanets is that the planets we've discovered so far display an extraordinary diversity in terms of their orbits, masses, and compositions. As you can see in this beautiful artist rendering of hundreds of exoplanets discovered by the Kepler mission. And also through radial velocity and statistical transit surveys like Kepler, we've also learned that the most common type of planet in the galaxy are planets between the size of Earth and Neptune, so-called super-Earths and mini-Neptunes, as you can see in this occurrence rate plot from Pettigrew et al. And as you can see in this also artist illustration showing different super-Earths discovered by Kepler with the Earth for reference. And these are planets for which there are no solar system analogs. And so these objects are quite mysterious. So one of the most compelling questions that we can ask about these planets is, what are they made of? Are they scaled up versions of Earth or scaled down Neptunes? For the giant planets that we've discovered so far, we have a pretty good handle on what they're made of. Just based on their masses and radii, we can tell that they're primarily composed of hydrogen and helium and other gases. And we've even detected some atomic species, metal species in their atmospheres, as you can see in this transmission spectrum from Watanabe et al. But for the smallest planets, they still remain largely a mystery in terms of their composition and their atmospheres. And so the main question is, why is exoplanet structure important? And from the point of view of planet formation, we know that the diversity of exoplanets that we see reflect multiple formation pathways. And so if, learning more about the potential structures and types of planets and their frequency will shed light on planet formation theories. In addition, we know that the properties of the planets that we observe today are not only determined by the conditions at birth, but also by the evolutionary processes that shape and sculpt them, such as photoevaporation, mantle stripping, migration, and so on. And so constraining the frequency of different types of planets will give insight into the different evolutionary processes that they undergo. And finally, one of the most important questions is, are we alone? And one of the holy grails of exoplanet science in particular is the search for life and the search for another Earth. And right now, we're at the point where we can measure the main bulk properties of a planet, like the mass and the radius. But in order to really be able to constrain if a planet is habitable, we're going to need to understand their interior structure, what they're made of, and be able to predict things about the interior, like their core mass fraction, whether they have magnetic fields, because all of those things are crucial to the potential to harbor life. So when we plot the distribution of exoplanet sizes, we also find a very notable feature. Namely, we see a gap in the radius distribution at around 1.8 Earth radii. And our current interpretation of this gap is that this gap marks the separation between planets that are rocky, so predominantly made of rocks and silicates like the Earth, and planets that are gaseous, which are massive enough that they were able to accrete and retain large envelopes of hydrogen, helium, and other gases like methane and ammonia. However, in reality, exoplanet compositions are a bit more complicated because planets, and especially small planets, are really diverse in terms of composition. And so to show you that, this is a mass radius diagram showing planets, small planets discovered prior to 2015. And the different colored lines that you see here are theoretical mass radius curves for planets made of different raw ingredients. So for example, if you follow this blue line on top that says 100% water, any planet falling along this line could in theory be made of 100% water. Although this is of course not physical, but it's used as a reference. But what I want you to notice is that planets that are roughly less than about 1.5 or 1.6 Earth radii generally follow compositional lines that are consistent with mixtures of rock and iron. Whereas planets that are a little bit larger than that are sort of occupy a larger region of parameter space, which reflects multiple formation and evolutionary pathways. And this, you can see that planets larger than that are in general more diverse, but also more uncertain in terms of their composition. And so one corollary is that we will need very precise masses and radii in order to constrain the composition of the smallest planets. So to give you an idea of how well we're doing right now, currently we have about 350 exoplanets that are less than 4 Earth radii, with masses and radii uncertainties of less than 50%. And this is pretty good for a lot of planets, but we hope to do better than that in the future in order to really constrain exoplanet atmosphere compositions and atmospheres. And right now, the best measured exoplanets have about 4% and 2% uncertainties in their masses and radii. So this is the best that we can do right now. But even if we knew the planet's mass and radius perfectly well, small planets still suffer from this pesky degeneracy in their density and composition, such that planets of a given density could have different interior structures. And you can see that in this you can see that illustrated in this schematic showing 4 hypothetical planets that all have the same mass and radius as the Earth. And from the outside, if you just measure their density, you wouldn't be able to tell what their interior structures are like, but they could be, made up of all these different layers. And so, so there are these degeneracies that we have to deal with small planets. And in addition, there are also uncertainties in the equations of state of materials that complicate the picture. But the bottom line is that mass and radius of a planet are not enough to constrain its composition. And so we're going to need another variable in order to understand this better. And so one way to break or reduce the degeneracy in exoplanet density and composition is by using the chemical composition of the host star, and in particular, the abundance of iron, magnesium, and silicon to constrain these compositions. And the rationale is that stars and planets form from the same molecular cloud and of gas and dust. And so that because of this common formation origin, we expect that rocky planets would reflect the composition of their host stars. And the basis for this assumption comes primarily from the observation that the bulk composition of the rocky planets in the solar system, except for Mercury, reflects the relative abundances of the major rock-forming elements in the sun. And in particular, the Fe upon mg and Si upon mg ratios are similar in the sun and in the planets of the solar system. And there also this, we've also observed that the composition of Ci chondrites, which are the most pristine and primitive objects in the solar system, also closely match the abundances in the sun. And so many authors have investigated these links between exoplanet composition and the chemical composition of their host star. And so here I'm highlighting a recent one that was very interesting by Adibekian et al. So they had a sample of 28 planets, and they measured the planets' densities and iron mass fraction, as well as the iron mass fraction of the host stars. And they found a very strong positive correlation between the planet's density or iron mass fraction and the stellar abundance of the host star. And these are other studies that you can check out if you're more interested in that connection. So now I want to swift gears a little bit and just talk about the core mass fraction because it's a very important property that I'll be talking about in the rest of the talk. So the core mass fraction of a planet is essentially the mass of the core divided by the mass of the planet. And this is very important because it controls the physical properties of the planet, such as the total mass that the planet is able to accrete during formation, as well as the strength of the magnetic field and the presence of an atmosphere. And all of these properties are directly related to a planet's habitability. And so that is one of the things that I work on and that I try to constrain in my research. But so I told you about how we're going to use this variable of the host star abundances to constrain composition. And so here is the framework that I follow. So essentially, I employ this framework that combines the planet's mass and radius with the stellar chemical abundances of the host star. And so what we do is I calculate the core mass fraction that is inferred from the planet's mass and radius, and I call it CMF rho. And I also measure the core mass fraction that is inferred from the from the star's chemical abundance, and I call that CMF star. And the idea is relatively simple. We have these two quantities and we compare them. And if CMF rho equals CMF star, then we can say that the planet likely has stellar refractory abundances and lacks an appreciable atmosphere. If CMF rho is less than CMF star, then we say that the planet has likely a measurable atmosphere. Whereas if CMF rho is larger than CMF star, then we can say that this planet is probably overly dense and has undergone some process that we don't know that resulted in this iron enhancement. And we don't know what this process could be, so we just playfully call it mercurification. And if you're more interested about this framework, I encourage you to check out this paper by one of my collaborators for more details. But so now I'm going to give you a brief overview of how we determine these two main quantities, CMF rho and CMF star. And I'm going to start with CMF rho. And as I told you, CMF rho depends on the planet's mass and radius. And so to get the planet's radius, for example, you need to have a planet that transits or that passes in front of the star from our point of view. And so for that, we use the transit method. And so the transit method, essentially, you wait for the planet to pass in front of its host star. And as it does that, it periodically blocks a fraction of light that we can measure as a dip in the light curve of the planet. And if we can measure how deep how deep this dip is, and we know the size of the star, then we can infer the radius of the planet very trivially through this the ratio of their radii. And then, so that gives us the planet radius. And then with the for the planet's mass, we instead use the radial velocity method. And in this case, what we're doing is we're measuring the shift in the Doppler lines of the spectrum of a star, which is caused by the planet itself wobbling sort of back and forth from our point of view, caused by the planet orbiting around it. And in this case, what we're measuring is the sort of amplitude of that the planet causes or induces on the host star. And from that, we get, we need to know the planet's eccentricity and the period. But from this, we get an upper limit of the mass. So we get the MP sin I of the planet. And so once we have the exoplanet data, we need to globally model all these data in a self-consistent way. And so for that, in my research, I use the open source IDL software ExoFast V2, which uses a differential evolution Markov chain Monte Carlo algorithm. And ExoFast 2 is a really great tool. It can simultaneously fit multiple transit and radial velocity data sets. And it can also fit multi-planet systems, as well as fit the star by itself. So it fits a SED to the star without the planet. So you can get very precise stellar parameters with very small uncertainties in their properties. And so the way I do this is I typically characterize the star first within the ExoFast framework, and then I use those as stellar priors, for the global fit. And then, so to calculate CMF star in general, I use the open source software Exoplex, which is a tool written by Kamon Unterborn and Wendy Panero, both at Ohio State. And essentially, this tool solves the differential equations of planetary structure, and it gives you a core mass fraction given a planet's mass and radius. And it also gives you the depth-dependent density, pressure, and temperature profiles of a planet, as you can see in this representative plot that I put here. And for these calculations, Exoplex assumes that the planet is a two-layer rocky planet with a pure solid iron core and a silicate mantle that is free of iron. And then for the core mass fraction, the CMF star, we use this equation that, as you can see, you don't need to remember any of this, just to, that for this calculation, you do need to know the FE upon H, SI upon H, and MG upon H of the star. And so for that, because the stars that I work with don't always have these abundances in the literature, I derive them myself using this software called iSpec, written by Blanco Quaresma et al. And this is a really great and user-friendly software that essentially gives you stellar atmospheric parameters as well as elemental abundances for F2K stars. And for that, it uses, you can use both the equivalent width method, in which here you're measuring sort of the equivalent width of the spectral features in order to determine all the properties and the abundances, as well as you can also use the synthetic spectral fitting method, which essentially fits a spectrum, a theoretical synthetic spectra to your spectrum. And so this is just an example of what it looks like. And so this is a real spectrum in blue. And the different vertical lines are just showing, are the atomic lines that are used for the process of determining the abundances. Okay, so now I want to introduce a type of planet that have been recently discovered called super-Mercuries. So these are planets that are very highly dense, sometimes even denser than the Earth. And so you can see them here sort of clustered in this density versus abundance plot. And so we know that in the solar system, the Earth, Mars, and Venus have core mass fractions of about 30%, whereas Mercury is a bit of an oddball in that Mercury has a much larger core and core mass fraction of about 70%. And we don't really know if Mercury was formed with this much iron or if it was sort of became iron enhanced through some post-formation process like mantle stripping or bombardment. But we have seen a handful of these very high density exoplanets, and we think that they may be perhaps consistent with a Mercury-like composition. And so these are some of the ones that we have found both in K2, in Kepler, as well as in TESS, which is this HD planet here that was very recently found by the TESS mission. And so now I want to talk to you about my research and what I've been working on in the past couple of years with here at OSU. And so this is one of the densest planets that we've discovered so far. This is an ultra short period planet. It has only a period of about half a day. And so it's called K2106b. This planet was originally discovered by Adams et al. And Adams et al. Was only able to place an upper limit on the mass of this planet of about 8.3 Earth masses. And so they were not able to constrain the density of the planet. But later reanalysis by Gunther et al., they were able to collect multiple radial velocity data sets, and they were able to constrain a mass. And they inferred a density for this planet of 13.1 grams per cubic centimeter. And for reference, the Earth's density is 5.5 grams per cubic centimeter. So you can see that this object is very highly dense, much denser than the Earth. And they also went ahead and calculated the core mass fraction of the planet, and they got a value of 80%. And remember, for Mercury, it's only 70%. So this seems to have an even larger core mass fraction than Mercury. And so what I'm showing here is just a plot from Gunther et al., a mass radius diagram showing that K2106b, which is represented here by the black filled symbol, falls on top of the 80% iron line. And so this is a really interesting planet if its density and its mass are indeed what they claim. And so I got really interested in the system, and we did some preliminary work on it, and we found that we could reduce the uncertainty in the planet's density if we correctly reanalyze the system in a self-consistent way. And in addition, we were also motivated by the improved parallaxes from Gaia-DIR2, which gives us an improved estimate of the planet's radius through the stellar radius. And so the idea was to combine planet interior models with this new statistical framework in order to ultimately assess whether K2106b is a true super-Mercury. And so for this project, I used existing photometry and radial velocity observations from Gunther et al. And specifically, I used K2 light curve and 6 radial velocity datasets. In addition, I used the open source software ExoFast, which I described earlier, to globally model the system. And within ExoFast, I used the MIST stellar evolutionary models to constrain the properties of the star and to use them as priors for the global fit. And here on the right, I'm showing the light curve, the K2 light curve of the system, where the data points are shown in black, and you can see the best fit model in red, and you can easily see the transits that are caused by the 2 orbiting planets in the system. So I didn't mention it earlier, but this is actually a multi-planet system. So there are 2 identified planets. The one that I'm focusing on is the innermost planet at a period of half a day, but there's another outer companion at a period of 13 days. So here you can see both of their transits in this light curve. And so this is the result of our global fit. On the left, you're seeing the transit light curve, phase folded by the best fit period found by ExoFast. And from the depth of the transit, I should say, so what you're seeing here is basically the data is in black, and then the model is in red, and on the bottom panel is just the residuals. And so from the depth of this transit and the size of the star, we infer a radius of 1.7 Earth radii. And then on the right, what I'm showing is the fit to the radial velocity data sets, and they're again phase folded by the best fit period with the residuals on the bottom. And so from this, I infer a mass of 8.5 Earth masses. And so, so here I'm showing the main derived parameters for this planet next to the values from Gunther et al., who found similar values. You can see basically we get consistent results except for the radius, because I get a slightly larger radius for the planet with smaller error bars. And so because we get sort of the same mass, but just a bigger size for the planet, then this infers that this leads to a lower density. And so I get a density of 9.4 grams per cubic centimeter for this planet, in contrast to Gunther et al., who got a much larger density, as you can see here. But we were also able, to shrink the error bars on the density as predicted by our previous work. So that was exciting to see. All right, so so now that we have the main bulk parameters for K2106b, the next steps were to calculate CMF rho and CMF star for this planet. And so for CMF star, we didn't, remember we need the abundances of magnesium, iron, and silicon. And so, but for this planet, we didn't have these from the literature. And so I went ahead and calculated them using a publicly available HARPS spectrum with very high resolution. And so you can see the spectrum is here shown in blue, with the yellow vertical lines being the atomic lines that are used for this calculation. And for this, I used the iSpec software, and I used the synthetic spectral fitting method to calculate the abundances. And for this, I basically adopted the stellar parameters that I got from ExoFast as initial guesses for the determination of the spectroscopic stellar parameters. And so I end up with these abundances for each of the species. So you can see that the star is pretty much close to solar, except it's a little bit depleted in iron. But these are the abundances that I get. And so with these abundances, we're then able to go ahead and calculate CMF star. And so these are the molar ratios that I get for the star. And I get a CMF star of 29%. Now remember, CMF rho, I'll say that next. But so CMF rho, again, using exoplex, we calculated that, and I got a core mass fraction rho of 45%. And so 45%, if you remember that the Earth's was about 30%, then this is already hinting both the density that we get of about 9 grams per cubic centimeter and the core mass fraction of 45% already hints that this planet is perhaps a super-Mercury, or at least it's iron enriched. But we still cannot be able to tell. We still cannot tell for sure. So now that we have all the elements in place, we have CMF star and CMF rho for this planet, we're ready to answer the question of whether this is a true super-Mercury. And so what I'm showing here is the posterior distribution function of the core mass fractions, both CMF rho and CMF star. for this planet. And so the black Gaussian that you see here is the core mass fraction that is inferred, the CMF star that is inferred from the stellar abundances that I derived using iSpec. And then in red is the core mass fraction star that if we instead use the reported stellar abundances from Adibekian et al. And here the purple distribution is just the core mass fraction rho that we derive of about 45%. And so remember earlier I told you that what we're looking for in this framework is we care about this comparison between CMF rho and CMF star. And I said if they're equal, the planet likely has solar refractory abundances and so on. But it's actually not as simple as, if they're equal or not. In mathematically, what we're actually interested in is computing the probability that the planet reflects the refractory elemental abundance of the host star. And we can quantify that by the overlap between CMFs, the distribution of CMF rho and CMF star. And so in general, the greater the amount of overlap, or the greater the overlap between these two distributions, the greater the probability that the planet reflects the composition of its host star. And so in this particular case, since K2106b, we think that it could be a super-Mercury. If it were a true super-Mercury, then we would expect these two distributions to be pretty disjoint or to have a pretty small overlap. And that would tell us basically that it has a very low probability of reflecting the host star abundances, which is what we would expect by definition. And so, and more specifically, in our framework, we assert that if this overlap between CMF rho and CMF star, or this probability, is less than 32%, then the planet deviates from the host star at the 1 sigma significance level. And so, if it's less than 32% in this case, then we would expect it to not be a super-Mercury. Or sorry, we would expect it to be a super-Mercury if it's less than 32%. However, as you can see already by eye, there is quite a bit of significant overlap between CMF rho and CMF star. And so, and we actually, when we do the numbers, we calculate an overlap or a probability of 60% for the pair of CMF star and CMF rho derived for this work. And as you can see also by eye, we calculate an even greater overlap of about 80% using the CMF, if we instead use the CMF star from Adibekian from the literature. And so what does that tell us basically? Here I've also plotted the CMF that Gunter got for reference, as well as the CMF of the Earth. And you can see that this planet lies sort of roughly in the middle of these two. But the conclusion is that although K2106b is a highly dense planet and probably iron enriched, we cannot conclude that it is a true super-Mercury given the uncertainties in its mass and radius and the uncertainties in the host star abundances based on this formalism. And instead, our analysis suggests that K2106b is more consistent with an Earth-like composition. And in fact, if we plot all the mass and radius measurements from the literature and from this work for K2106b in this mass and radius diagram, where again, these different lines correspond to the different compositional lines that planets could have. Again, just to remind you, if a planet were laying anywhere on this line, on the 50% water mantle line, that would mean that the planet likely is made of 50% water, 50% silicate mantle. But so when we plot K2106b on this diagram, we see that all the measurements place this planet sort of on top or very near the Earth-like composition line. And only one of the measurements, this purple data point from Gunter et al., places it below the Mercury line. And we now know that Gunther very likely underestimated the size of the star and therefore the size of the planet, and that led them to to infer a much larger density and core mass fraction than this planet actually has. And so, okay, now I want to move on to another part of the talk about different types of planets. So now that we successfully applied this methodology to a super-Mercury candidate, one of my research aims going forward is to apply and extend this methodology to a larger sample of exoplanets and eventually to longer period planets, which could be in the habitable zone of their host stars. And so far I've only talked to you about these super-Mercuries, but if we go back to the mass radius diagram, remember there's a huge diversity of exoplanet structures. And so one of the things that we find is actually things that are completely opposite to Mercury. So instead of being ultra dense, we find things that are very low density, and I've highlighted them here. We call them super puffs. So these are planets that are have pretty large radii, but relatively low masses. And so these planets have very low bulk densities of about 0.1 grams per cubic centimeter. And so this is another type of planet that is sort of a mystery, because we don't expect these planets to be, very large, have large radii, but small masses. And so this is another type of planet that I'm interested in investigating in the future. And in particular, one example of such planets is the very well known and characterized 55 Cancri E, which is another ultra short period planet, has a really, really high equilibrium temperature. And so this is a planet that was investigated by one of my collaborators applying this same framework that I'm describing. Essentially, they calculated the core mass fraction rho and CMF star for this planet. And you can see, so this is basically on the right, I'm showing basically the same plot that I showed you earlier for K2-106b with these two distributions of CMF rho and CMF star. But you can see that unlike K2-106b, the sort of area of overlap between these two distributions is pretty small. And so, and indeed, they calculate a core mass fraction star of 31%, whereas they get something like 0.1 or 0.4% for the core mass fraction as inferred from the planet's density. And so from this, they find this an overlap or a probability that the planet reflects the abundance of the host star of only 9%. And if you remember, in this framework, if it's less than 32%, then we assert that the planet deviates from the host star abundances. And so in this case, they end up concluding that this is a very low density, a small planet. And so this is another way in which our framework can be used to determine the structure of small exoplanets. But so besides 55 Cancri E, there's a bunch of really other interesting planets that have been previously discovered, and they already have, well-measured masses and radii, so they're ideal targets to test this framework on. The only little problem is that for a lot of these planets, we are missing their refractory elemental abundances. And this is sort of a problem in exoplanet science, where people they have spectra of their host stars, and they derive the TEF, the log G, and the main stellar parameters, but they only calculate Fe upon age. And so one of the things that I encourage the community is to provide these abundances so that we can make further progress on this field. But just so here I'm showing some of the targets that we've thought about, and this is work being led by one of my collaborators at OSU. And these are some of the planets we're hoping to be able to actually confirm one of these super-Mercury candidates that I told you about earlier, or continue killing some more candidates. But they're also really, there's potential to find even more interesting classes of planets with this methodology. And so to sort of conclude, I wanted to bring up work that I'm looking forward to in the future. And so one of the things that I wanted to talk about is the Transiting Exoplanet Survey Satellite, or TESS. So as you probably know, this is an all-sky transit survey that's covering over 80% of the sky in the optical and infrared. TESS is very sensitive to small planets. And one of its main science goals was to measure the masses of 50 planets of less than, with radii less than for Earth radii. So this is very exciting for the type of research that I'm doing. And TESS has already met that goal. We've already found over 50 small planets that have mass and radius measurements. And the exciting thing for my research in particular is that with TESS, something we can do with TESS that we can't really do with Kepler planets is that unlike TESS, or unlike Kepler, which was a statistical mission, TESS is focusing on the nearest and brightest stars. And so that means that almost all the targets found, all the planets that TESS will find are going to be very bright, and so they're going to be amenable to follow-up observations. And one of the ways in which we can test this statistical framework is by finding planets that have for which CMF rho is less than CMF star, sort of like 55 Cancri E, in which our model predicts an appreciable atmosphere. So because this planet is going to be, or this star is going to be relatively bright, we can go ahead and actually observe it with James Webb, which is already launched, and see if there's actually an atmosphere for this planet. And so that's work that I'm excited about in the future. And another venue that's possible with TESS that's exciting is that TESS will be also observing hundreds and finding hundreds of planets around M-dwarf stars, which are cooler and smaller than the sun. And one of the observational advantages of M-dwarfs is that because they are smaller than the sun, a planet of a given size will induce a smaller photometric signal. So we'll have so for the M-dwarf, we will have a larger transit depth, and so planets are easier to find around M-dwarfs. And in addition, because M-dwarfs are less luminous than sun-like stars, their habitable zones, which is the area where liquid water could exist on the surface of these planets, are also closer to the star, and therefore they increase the probability of small planets to transit, or the planets that are going to be transiting are going to be more likely to reside in this habitable zone. And but the main thing is that M-dwarf planets are also ideal for the same reason, because they're smaller. They're ideal targets to search for atmospheric characterization and to search for biosignatures with James Webb. And so, in conclusion, I just want to say that in order to really find this an Earth 2.0, we're going to need an interdisciplinary approach where we investigate all aspects of the planet, not just, to first order the temperature and the size. We're going to need to know about their interior structure, the plate tectonics, volcanism, and all of those things. We're going to need a framework that can give us all these parameters, and that's how we're going to really be able to constrain the properties of the smallest planets in the coming decades. And so in conclusion, we performed the most thorough characterization of the known super-Mercury candidate K2106b, and we find that it is unlikely to be a true super-Mercury. And my work also suggests that it's perhaps other Mercury candidates in the literature may not be as iron enriched as previously thought, or even super-Mercuries. And to robustly determine the composition of the smallest planets, we're going to need very precise masses and radii, and often even multiple radial velocity data sets, as I've shown in this work. And we are also going to need the refractory elemental abundances of the host star, magnesium and silicon, to constrain exoplanet composition. And so I do encourage the community to provide these for planet hosts when they're able, so that we can make further progress on this field. And in the future, I will extend the statistical framework to planets discovered by TESS and on longer periods, and possibly planets around M dwarfs discovered by TESS. And eventually, my work will help build a ranked list of targets to prioritize for future atmospheric characterization. And so with that, I thank you for your attention, and I'll take any questions.
Great, thank you, Romy, for a really nice talk. And we do have plenty of time for questions. In fact, I think, Andy, you had one that you put in the chat and I missed. I'm sorry, but if you want to go ahead and ask it now.
Oh, I sort of wish I hadn't put that in. It's you were quoting very small abundance uncertainties, and that's just kind of as good as you can get. So it kind of surprised me that, you know, just pumping a spectrum into a pipeline kind of a program, that you'd get that good, but you know, maybe. But I agree, having very accurate abundances is important. But I wanted to share my screen if I could.
Of course.
Yeah. Thank you. I know that's weird, but so I wanted to show you this particular plot, if you can see it.
Yes, I can see it.
Okay. And so what this is FGK stars in the Milky Way. The red points are thick disk, mostly thick disk, and then the black points are mostly thin disk. And these are averages of 3 elements here: silicon, calcium, titanium. This is magnesium, oxygen. What you can see, it's a pretty tight trend, and part of it is because those elements have been averaged. But you know, you asked for very precise abundance ratios, and I don't know why you couldn't just get your ion abundance, use the kinematics to determine whether you're in the thick disk or thin disk, and then just say, well, you know, like this is the composition, and you're going to be within, you know, a similar measurement uncertainty. So you know, just from the galactic chemical evolution of the thick and the thin disk, you know, the scatter at a given ion abundance, I mean, I think this is mostly observational anyway. So I don't know what, you know, why you would go out and take a spectral, yeah, and go through all that effort when I'm not sure you can do much better than that. And I'll stop sharing that now.
Yeah, thank you. That's a great point. Thank you for showing me that. The reason we wanted to go ahead and calculate these abundances for this particular star is because it didn't have abundances from in the literature. So this are I think my paper is going to be the first one to report these abundances. So we wanted to do that. And the other reason is we already had a high resolution spectrum, and so we thought it would be, you know, a good idea to make use of it. And also was a fun, you know, I started dabbling into spectroscopy, and I also learned a few things by using this program. And so I think that was useful for me personally.
So, and then related to that, I mean, how did your abundances compare with these trends? These are Bensby trends, but how did they compare? Did you feel like you got a significantly different result than these galactic trends?
I'm not sure. I'd have to look at these trends a little bit more, but I think when I looked at the silicon and magnesium trends, like for stars in the galaxy, I think it was similar, or you know, it was consistent with what I expected. So it's a very regular sun-like star.
Okay, thank you.
Let's see, Elva, you had a question?
Yes, I want to say first, thank you so much. It was very clear and interesting presentation. I don't work with planets, so it's also really nice to learn some new things. I wanted to ask, because I could notice in some of your plots, especially towards the first part of your presentation, that you had a different result depending on whether you account for this model of the star, the mist model, or not. I wanted to ask if you could explain a little bit more what exactly in the mist model is it that makes a difference, and like why is there, like, what's the difference just in the technique there?
Yeah, thank you. Thank you for your question. So yes, so in this paper, this paper is kind of a follow-up to an earlier work in which we showed that we could get comparable precision on the stellar parameters if we just, you know, model the star almost fully empirically. So just using a star's SED and a parallax from Gaia, as if we used stellar models from, you know, like MIST or Yonsei-Yale isochrones. And so the idea was that, you know, if we could use, so we wanted to test this sort of, and we wanted to see if we could get sort of the same or comparable precisions. And that's why in this work, I modeled the star and the system both with using constraints from the MIST isochrones and without. And using the MIST isochrones, we do get slightly more precise stellar parameters, but that's because you're using, you know, constraints from stellar models. Whereas if we don't, we get slightly larger uncertainties, but we think that those are more robust because those are direct, you know, from direct observations of the star. And so that's the difference. But we do get consistent results. It's just like, and for the paper, I'm planning to report the stellar and planetary parameters from both using MIST and without MIST.
Right. So basically, without the MIST model, it would be model independent, the results.
Exactly.
Correct?
Yes.
Oh, that's really nice. Okay, thank you.
Enrique, do you have a question?
It is actually, sorry. Oh my God, sorry. Just a second. It is actually more of a comment than a question. So it might, I might comment on what Andy said too. So Andy asked about the uncertainties. So when using ISPEC, Andy, it really codes really small uncertainties because the EW measurements that it makes are really consistent with each other. So that's why the uncertainties that comes out of ISPEC are usually that small, but we can talk about that later.
So like 0.02 dex in FE is roughly 20 Kelvin.
Yeah,
so
it does say that.
Due to 20 Kelvin.
I mean, I don't want to say anything about accuracy, but the measurements of the individual equivalent weights are usually very, very constraining.
It's very impressive that just by bunging it in there, you can get as good as a lot of hard work.
There is a paper by Tuchimaya, like, if I remember correctly, 2016, that compares ISPEC with ARES, the code that the group from Porto use, and using S-plots directly from IRF, and he talks a little bit about this, and I can send that to you later. Also, I just wanted to mention that on the topic you guys were discussing of either or not just use chemical evolution to constrain the chemistry of the stars, I would argue against that, because I think that for planet hosts, there might be chemical differences that cannot be accounted for by chemical evolution alone. So I would actually argue that the steps that you are taking are important in this case.
Thank you. I agree.
So,
yeah.
Those are two comments, and I could also comment on Eva's question too, that mist isochrones, because they are solar scaled, then, and these stars are usually close to solar composition and evolution, then that's one of the reasons why the fittings are precise on this particular set of models. So these were comments, not questions. Really nice presentation, by the way.
Thank you.
Well, let's see. I think we have a question from Jason.
Yeah, can you hear me? Yes. Okay. Yeah. So thanks for this really great presentation. Really interesting to me. I just wanted to know if you could comment on, or if you could speak at all on how where the planet forms in the protoplanetary disk plays into this formalism, or if you have any plans to incorporate that at all.
Yeah, that's a really interesting point. I have not thought about it, but of course, yes, it does matter where the planet forms in the disk for sure. It's just something that I don't think it's specifically or like explicitly in the models that I'm using, but.
Oh yeah, I was just curious. Yeah, but yeah, thank you again for your presentation. It was really great.
Thank you.
All right, do we have any last questions? Okay, I don't see any. So in that case, let's thank Romy again for a really nice talk. And thanks
Thank you.
everyone
That
else
was
for joining us.
great. That was great, Romy.
Thank you.
Thanks
Thanks,
everyone.
Andrew.
Bye.
Bye.
Thanks very much. Thank you.